Hi, my name is Lindsay Taff, and today I will be discussing the indirect effects of aerosols on clouds and precipitation. Clouds contribute to our everyday lives in both direct and indirect ways. Clouds, first and foremost, are immediately visible in the sky, but more importantly, clouds play a crucial role in the global energy and water budgets that determine the Earth's climate. Clouds contain substantial amounts of water in both the liquid and solid phases that are able to dissolve gases and permit reactions to occur that would not otherwise or would occur at a slower rate. Clouds then serve as a catalyst for atmospheric reactions. An aerosol is defined as a colloidal suspension of particles dispersed in air or gas. These particles are also referred to as particulate matter, PM 2.5 or PM 10, depending on their size. Key aerosol groups include sulfates, organic carbon, black carbon, nitrates, mineral dust, and sea salt. In this animation, red represents dust, which can be seen blowing over the Saharan desert and interacting with two Atlantic tropical cyclones. The blue depicts sea salt that is whipped up from the ocean by surface winds. It is most prevalent along mid-latitude storm tracks and fronts in the Southern Ocean and within tropical cyclones. The green mass represents organic and black carbon from widespread biomass burning in South America and Africa. The color white represents sulfate, which arises from three primary sources: fossil fuel emissions over Asia, Europe, and the United States. The bulk of aerosols, about 90% by mass, have natural origins, while the remaining 10% are considered anthropogenic. Aerosols can interact with clouds and precipitation in numerous ways. Aerosols can act as cloud condensation nuclei, ice nuclei, or absorbing particles that redistribute solar energy as thermal energy within cloud layers. Clouds in clean air are composed of a relatively small number of large droplets as shown on the left side of the diagram below. As a consequence, the clouds are somewhat dark and translucent. In air with high concentrations of aerosols, water can easily condense on the particles, creating a large number of small droplets as shown on the right side of the diagram. These clouds are dense, very reflective, and bright white. This influence of aerosols on clouds is called the indirect effect, and is a large source of uncertainty in projections of climate change. Indirect effects are defined as the mechanism by which aerosols modify the particles within clouds, affecting the radiative properties in lifetime. These indirect effects can be subdivided into different contributing processes as shown below. The first process we're going to look at is the cloud albedo effect. The cloud albedo effect occurs when enhanced aerosol concentrations, under the assumption of a fixed water content, lead to an increase in small cloud droplets, resulting in more reflection of solar radiation. This results in brighter clouds, which in turn block the sunlight from reaching the Earth's surface, shading it and producing a net cooling. This aerosol effect is clearly seen in ship tracks, chemtrails, and contrails. These bright streaks in marine clouds can be formed by exhausts containing sulfates and other aerosols, or by natural aerosols such as sea salt or ammonium salts. The next process going to be discussed is the cloud lifetime effect. This occurs because the smaller cloud particles decrease the precipitation efficiency, thereby prolonging cloud lifetime and resulting in more reflection of solar radiation. The smaller particles make it so that precipitation is diminished or suppressed depending on environmental conditions and cloud type. By diminishing the rainfall, the lifetime of the cloud changes, and it takes longer until the cloud rains and disappears. The longer lifetime of these contaminated clouds lead to an overall increased cloud cover, reducing the net solar radiation at the Earth's surface, producing a cooling effect. Since the aerosols affect the total amount of precipitation, they also reduce vital water sources. This can cause drier soil, creating more dust that will in turn start this process over. This can be referred to as a feedback loop. Now, we are going to look at the semi-direct effect. This is due to the absorption of solar radiation by black carbon within a cloud. This can significantly affect cloud lifetime. Due to this absorption, the evaporation of water droplets within the cloud is increased, which leads to a decrease in cloud cover. The temperature is also increased, which in turn reduces relative humidity. These affect the thermal atmospheric structure and dynamics, and contrary to other aerosol effects, amplify the warming effect of the Earth atmosphere system. The graphic below shows that black carbon aerosols absorb sunlight rather than reflecting it. This warms the layer of the atmosphere carrying the black carbon, but also shades and cools the surface below. Here we look at the glaciation indirect effect. The glaciation indirect effect refers to an increase in ice nuclei within the cloud, resulting in a rapid glaciation of a supercooled liquid water cloud due to the difference in water vapor pressure over ice and water. Unlike cloud droplets, these ice nuclei grow in an environment of supersaturation with respect to ice. These quickly reach precipitation size that can turn a non-precipitating cloud into a precipitating one. This effect is linked to black carbon aerosols that act as effective ice nuclei. This entails a higher precipitation efficiency and shorter cloud lifetime, counteracting the aerosol indirect effects on warm clouds. The last process we are going to cover is the thermodynamic effect. This process affects mixed phase clouds. The thermodynamic effect is when there is a delay in freezing by the smaller droplets, causing supercooled clouds to extend to colder temperatures. Small droplets have a low collision efficiency and a low immersion freezing probability. It was shown that the suppression of a warm rain formation and the delayed freezing in polluted clouds result in increased latent heat release by freezing at higher altitudes, invigoration of convection, and triggering of secondary clouds in the vicinity. This effect is termed thermodynamic effect because the anthropogenic aerosols are assumed to influence the thermodynamic structure of convective clouds. Scientists use an array of satellite, aircraft, and ground-based instruments to monitor aerosols. Radiometers, instruments that quantify the amount of electromagnetic radiation, are among the most important tools available. The key quantity they report is aerosol optical depth. Aerosol optical depth is the fundamental measurement of quantity and distribution of aerosols. This map shows the average distribution of aerosols from June 2000 through May 2010, measured by the multi-angle imaging spectroradiometer. Red indicates high concentrations of aerosols and beige indicates low concentrations. An optical depth of less than 0.05 indicates a clear sky with relatively few aerosols and maximum visibility, whereas a value of 1 indicates hazy conditions. Optical depths above 2 or 3 represent very high concentrations of aerosols. The figure below shows the overall things that are present in the atmosphere. Greenhouse gases are at the top and aerosols are in the box. The line down the middle represents radiative forcing. Anything to the right of the line represents warming, and anything to the left represents cooling. There are two take-home lessons from this figure. If you notice, the majority of greenhouse gases are to the right, representing warming. For the greenhouse gases, it is important to recognize the size of the uncertainty bars. They are short, which means that we have a pretty good grasp on what is going on there. However, when we come down to aerosols, the bars are to the left of the radiative forcing line, indicating cooling. In the case of aerosols, the uncertainties are way larger. These large uncertainties are due to the lack of understanding there is on aerosols. Clouds and aerosols continue to contribute to the largest uncertainty to estimates and interpretations of the Earth's changing energy budget. It is perceived that changes in the concentration of aerosols can alter the precipitation of clouds, thus changing the radiative forcing. Despite the extensive research on this topic, it has proved difficult to establish the exact relationship between aerosols, clouds, and precipitation.